The goal of this presentation is to provide an explanation of 3 different methods for finding the kth smallest element of a collection of integers. We will analyze asymptotic complexities and report on the efficiencies of each method. As I said, the problem we are solving is to find the kth smallest element in a given collection of integer numbers. The collection we used is a file containing 1 million integers ranging from 1 to 1,000. We will focus on the efficiencies for k values of 1, 100,000, and 850,000 in order to compare the 3 different methods. Method 1 uses a heap data structure. A minimum binary heap is a binary tree with a key in each node that satisfies the following 3 conditions. 1. All leaves are on at most 2 adjacent levels. 2. All leaves on the lowest level occur to the left and all levels except the lowest one are completely filled. 3. The key in the root is less than or equal to all of its children, and the left and right subtrees are also minimum binary heaps. To the right, you could see an example in the shape of a tree and also with the value saved in an array, which is how we actually work with heaps. In order to build our heap, we need to understand a procedure called heapify. Heapify takes an element, such as 9 in the diagram below, whose 2 children are each binary heaps, and bubbles down the 9 to its proper place. This turns the element plus its 2 binary subheaps into one heap. To build our heap, we first enter our 1 million integers into an array that represents a heap in the order they appear in the file. We then call heapify until our elements satisfy the heap requirement that each node is smaller than the nodes of its subtrees. This means calling heapify on half of the elements of the heap. Starting at the back of the array, we see the first element with any children is the middle element of the array, so this is the first element that we must call heapify on. We call heapify on that element and then each element in front of it until we reach the first element. Each call to heapify takes at most big O of log of n time, since log of n is the height of the tree, and this is the most times each element can be bubbled down. We do this n over 2 times, so it seems that this whole procedure takes big O of n log n time. We can actually use the fact that many of the elements we call heapify on will not actually take log of n swaps to bubble down. We can get a tighter upper bound using this information, giving us an upper bound of big O of n. When we find the minimum value of the heap, we want to extract it from the heap so that the next call to minimum gives the second smallest value. When we extract the second smallest, the next call gives the third smallest, and so on. So, to do this, we replace the minimum with the last element of the heap, and then call heapify on that element to move it to its proper place. This takes big O of log of n time, since that element may need at most log of n swaps to get to its proper place in the tree. When we find the kth smallest value, we build our binary heap using heapify, then call the minimum function k times. As we said, using heapify to create the heap takes big O of n time. Calling the minimum function k times takes big O of k times log of n time. So our total time complexity is big O of n plus k times log of n. Here you can see how long this method took for k equals 1, k equals 100,000, and k equals 850,000. As you can see, as k increases, so does the time that it takes. This makes sense because k is present in our asymptotic complexity, multiplying the log of n terms, which means as k increases, so will our complexity.
The second method we use to find the kth largest element number in a list of 1 million random integers is by using a binary search tree, or a BST for short. A BST is a type of tree that stores data in such a way that is meant to be efficient in sorting, searching, and retrieving data. In a BST, every node has at most 2 children. The left child is always less than its parent node, and the right child is always greater than its parent node. Also, there are no duplicate keys, or elements. Since we have a list of 1 million randomly generated numbers, and the numbers themselves only range from 1 to 1,000, it's inevitable that we would have duplicate numbers, which are not allowed in a binary search tree. To circumvent this, we simply have a counter for each node in the binary search tree, and we use that to keep track of every duplicate of a number. Now when applied to our problem of finding the kth largest number in a set of integers, the worst case time complexity is O of n squared. The creation of the BST itself takes O of n squared time because inserting a number into the tree takes n time, and there are n elements to be sorted. Traversing through the data structure to find the kth largest element takes O of n log n time, because each level of the tree that you travel through, the number of nodes left to search is cut in half. However, this does not matter because the total time complexity for the algorithm ends up being O of n squared, because O of n squared plus O of n log n is still just O of n squared. In our experiments, as shown, you can see that the difference between finding the smallest value and finding the 10th smallest value were almost negligible. However, finding that 850,000th smallest value took significantly longer.
The third method we use to find the kth smallest number in a list of 1,000,000 random integers is Quicksort. The standard C library provides Quicksort that can be used for sorting an array. This is the declaration for the Quicksort function. It does not return any value. The parameters are base, n items, size, and compare. Base is the pointer to the first element of the array to be sorted. N items is the number of elements in the array pointed to by base. Size is the size in bytes of each element in the array, and compare is the function that compares two elements. The key point about Quicksort is this comparator function. It takes two arguments and contains logic to decide their relative order in sorted output. Moving on to the asymptotic complexity, Quicksort has an average and best case of O of n log n. This occurs when the array is rearranged into two similar length subarrays in each partition process. The worst case of Quicksort is O of n squared. This occurs when the array is rearranged into one subarray containing one element and the other subarray containing the rest, throughout every partition process. This generates an extreme split and results in slow performance. The k values we chose to test are 1, 100,000, and 850,000. The first one took 87,025 microseconds to complete. The second one took 86,055 microseconds to complete, and the third one took 84,519 seconds to complete. Since accessing an element takes constant time in an array, it makes sense that the three items are close in value. In conclusion, after testing the same k values in three different methods, we determined that all three Quicksort searches were faster than the BST searches. They were also faster than two of the three Heap searches. This is because every time we increase the value of k, the heap has to find and delete that many more times. We also discovered that the BST method proved to take the longest to complete. And this concludes our presentation.